Today we're looking at simplifying radicals beginning on page 511 in the textbook. We're using properties of radicals to simplify, and we're going to look at it in a real life type problem. First thing you have is a definition of what is the simplest form. The simplest form of a radical expression is an expression that has no perfect square factors other than 1 in the radicand, no fractions in the radicand, and no radicals in the denominator. Okay, so what it does is it gives you 3 questions that you have to ask yourself at the end of each radical to determine if it's in its simplest form. You know that 6/8 is not in its simplest form, just talking about fractions. You know you need to reduce that by the number 3. I'm sorry, by the number 2, and you get 3/4. So this is the simplified version of that. With radicals, we're talking about the simplified versions of those. So you ask yourself 3 questions. One of the questions are there any perfect squares? You have to ask yourself these 3 questions every single time that you do radical problems. Any perfect squares or any perfect square factors? Number 2, any fractions in the radical? And then number 3's question is any radicals in the denominator, and we know that that means the bottom of the fraction. If all 3 of those questions, if you can answer no to all 3 of those questions, then it's considered a simplified version of a radical. So let's take a look at a couple of examples. Actually, the first set of things is the properties. It says the square root of a product equals the product of the square roots of the factors. What that means is whatever's underneath that radical symbol, the radicand AB, you can separate it. For example, if you have the number 27 can be separated, and that's the one we're looking at right now, I believe. 27 in just a second can be separated into the square root of 9 times the square root of 3. You can separate them however you want. Whatever numbers that you can multiply by each other to get that number you want to you can separate with. But the only way you're going to be able to simplify them, the only way you're going to be able to change them and make them more user-friendly is to use what's known as the perfect squares. And we listed the perfect squares last week. But it's a good habit while you're doing this to list them out to make sure you use them. 2 times 2 is a perfect square, it's 4. 3 times 3, 4 times 4, 5 times 5. It continues like that. 6 times 6, 7 times 7, and it goes on and on and on. If one of those numbers multiplies by something to give you a number like 27, then you want to multiply it by that number the way you can simplify it. So notice it says where A is greater than or equal to 0 and B is greater than or equal to 0. So you're not talking about any negative values right here. The quotient property is the same exact thing, except it deals with, instead of multiplication, it deals with division. You're still, just like with this one here, we separated it from one number put together to 2 separate radicals multiplying by each other. You're doing the same thing with the quotient property. You're taking one radical underneath one fraction underneath a radical, and you separate it and making it 2 radicals on top of each other. But this is considered not simplified because the 3 questions, remember what the 3 questions were? One of them was that it can't have a radical at the bottom of a fraction like that. So that's part of what we're getting to. Again, not dealing with, right here telling you not dealing with any negative numbers. Let's look at that in an example. The square root of 27, I did that one just a second ago. It says you can use the product property to simplify a radical by removing perfect square factors from the radicand. Again, 2 times 2, 4. 3 times 3, 9. 4 times 4, 16. Those are the numbers that you have to know. Those are the numbers that you have to use. Which one of them are you going to, it continues to go on. I went up to 7 right there, but it continues to go on. Which one of those can you multiply by and get the number 27? We know that we can multiply 9 by it. So when you separate it, always put the perfect radical first, or the perfect factor first. And the reason you do that is since you always write the numbers in front, the coefficients in front, like 2x, you don't ever write that as x2. It acts just like a coefficient when you're talking about the radicals when we change it. We can separate that with its perfect square factor of 9 times 3. Again, it's written like this, I find it's way more helpful to write it as like a little tree. The square root of 9, square root of 3. That says the exact same thing as what I just circled. And then so that lets you see what times itself is the number 9. And again, it's talking about not negative values, just the positive principal ones. What times itself is 9? 3 is. So you have 3 times the square root of 3 is what it's going to wind up being. And that's its simplified version, 3 square root of 3. Take a minute to do square root of 48. Again, think of your perfect square factors. Okay, let's take a look at this one. It says the square root of 48. It's not a perfect square. So it's not one of these numbers I listed, 2 times 2, 3 times 3, 4 times 4, all the way up through 7 times 7. But one of those numbers, or more than one of them, multiplies by something to give you the number 48. Now we know, or some of us, or most of us probably know, that this is the best number to use. It's the larger one. It's the greatest factor that goes into it. But let's say you didn't realize that right away, and instead of using 16, you use 4. Can you multiply 4 by something to get 48? Sure you can. The square root of 4 multiplies by the square root of 12. So you have the square root of 4 times the square root of 12. We know that when we simplify what times itself is 4, we get 2 times the square root of 2. But we're not sure if this is going to be finished or not. The way we can determine if it's finished is we ask ourselves those same 3 questions from earlier. Are there any perfect squares? Are there any fractions in the radical, or are there any radicals in the denominator? As you're looking at this right here, there's no fractions at all. So it takes care of this one, and it takes care of nothing with a denominator. So the answer to both 2 and 3 are no. So check the first question. Are there any perfect square factors? Is there any one of these numbers, and again, those numbers continue to go up past 7 times 7. Can I multiply one of those numbers by something to get the number 12? We can separate it. 4 goes into it. The square root of 4 times what? The square root of 3. What you can't forget, however, is you can't forget to bring this 2 down. That'll be the mistake you'll make in something like this. You'll forget there's a 2 there. You bring it down just like I just did. It's not a radical. It's something that you're going to multiply by. So it becomes 2 times the, it's right next to this, so it's times the square root of 2. We know the square root of 2 is 2 times the square root of 3. And when you put those 2 back together, 2 times 2, you get 4 square root of 3. Again, asking yourself those 3 questions. There are no fractions at all, so 2 and 3 are out. Any perfect squares? No. There's none of these numbers multiplied by anything and give you the number 3. So that's why it's that's why it's considered simplified. Again, 16 would have been the best one. You would have did the square root of 16 times the square root of 3 and gotten 4 times the square root of 3. But just in case you didn't realize that 16 went into this right away, wanted to show you that 4 worked as well. Here's example number 2. Example number 1 dealt with the product property. Now these are the quotient properties because now you have fractions, the square root of 5 over 16. You separate it. The first thing you want to do is separate it and make it say the square root of 5 over the square root of 16. That's what you can do. This is not considered simplified because you cannot have a radical at the bottom of a fraction like this. Luckily, the square root of 16 is a perfect square. We know what times itself gives us 16. We know the number 4 times itself gives us 16. So once it's separated, the square root of 5 over 4. Then you just ask yourself the 3 questions again. Are there any perfect squares in 5? No. Those perfect squares don't multiply by anything to give you 5. Are there any fractions in the radical itself. Okay, now this is something, when people see this problem like this, they'll get this confused. They'll see the square root of 5 over 4, and they'll think they have to do something else to it because they think that there is a fraction under that radical. Notice what is under the radical. The only thing that's under it is 5. Over 4 is not underneath that little house. It's not underneath that radical. Only 5 is the radicand. So that's not considered having, it would have to look like it did originally, where it was, the whole thing was underneath it like that. Or it would have to look like this in order to not be simplified. But this is considered simplified, the square root of 5 over 4. The second one says the square root of 48 over the square root of 75. You have to do both of them this time. This time you got to separate it and make it say the square root of 48. I believe it's easier to do it this way, over the square root of 75. Now, we just did the square root of 48 a minute ago. We know that it's 16 times something. So when we separate this top part of the radical, we get the square root of 16 times the square root of 3 over, when we separate the square root of 75, we know its perfect square factors are 25, because we know quarters go into 75 cents. Think of it that way. 25 times the square root of 3. Now look and see what you have here. You have the square root of 3 divided by the square root of 3. What happens when you divide anything by itself? You get what? Yeah, you get 1. What's 2 divided by 2? That's 1. What's 22 divided by 22? That's 1. What's 222 divided by 222? It's still 1. So the square root of 3 divided by the square root of 3 is going to be 1. So now you have the square root of 16 over 25. They still have it together on that step. But it could look like, I have it here, the square root of 16 over the square root of 25. Again, both of those are perfect squares. What times itself is 16? We know it's 4. And what times itself is 25? There they are separated there. What times itself is 25? We know 5. So 4 over 5 will be your simplified answer. Again, asking yourself the 3 questions from earlier. Are there any fractions under the radical? Are there any radicals under a fraction or at the bottom of a fraction in the denominator? Or are there any perfect squares still factored in it? That's the 3 questions you ask yourself. Here's 3 problems. Answer these. Will give you about a minute or so. Okay, let's take a look at these 3 problems. You'll develop a whole lot more speed with these as you go. Remember, when you have the square root of a fraction like this, you can separate it, make it say the square root of 7 over the square root of 16. Now, there's no perfect squares that's in 7, but 16 is a perfect square root. So you have the square root of 7, it stays just like it is. What times itself is 16, we know is the number 4. Again, ask yourself the 3 questions. Are there any perfect squares in 7? No. Is there a radical under a fraction symbol like it was at the beginning, the great big thing? No. And is there a radical symbol at the bottom of a fraction anymore? No. So this is simplified. No, no, and no means it's simplified. B says the square root of 18 over 3. Okay? There's no radical at the bottom, so this one's good so far. But there is a perfect square factor in 19. We know 9 multiplies by something to give you 19. So the square root of 9 multiplies by the square root of 2 over the 3 that's already there. So it says the square root of 9 is what? That's 3. That's what times itself is 9, times the square root of 2 over 3. Now this says 3 divided by 3. Again, that cancels out to give you 1. So what you're left over with is simply the square root of 2. And then you can simplify C. It says the square root of 80 separate over 45, separated to make it say the square root of 80 over the square root of 45. Okay. Again, you might not know what's the best number that goes into 80, but you can ask yourself, well, does 4 go into it? Yeah, it does. The square root of 80 separates, and it might even be easier for you to do it this way. The square root of 80 and the square root of 45 to break them down. The square root of 4 multiplies by the square root of 20. So that's 2 square root of 20, which we can separate again. We know that the number 4 goes into that as well. So the square root of 4 times the square root of 5. 2 times 2 times the square root of 5. 2 times 2 we know is 4 square root of 5. So we could have right away said that 16 went into it if you knew 16 was a factor of 80. The more you work with these numbers, the more you'll get used to the ones that go into the other ones, because it'll just be a speed thing for you. And then the square root of 45 breaks down to perfect squares. 9 times the square root of 5 is it. So the square root of 9 is 3 square root of 5. So now we have to go back to this form because it was a fraction originally. So at the top we have 4 square root of 5 over 3 square root of 5. Again, anything divided by itself, you can see right here that it has the square root of 5 divided by the square root of 5. They cancel out and leave you with 1 over 1. So it's simply 4 over 3 is your simplified answer for that one. There's no radicals at all, so that's simplified. And then you have some checkpoint problems. The square root of 12. The square root of 4 times the square root of 3. Again, remember what your perfect squares are. 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7. It goes on and on and on and on. The square root of 4 means what times itself is 4? 2 square root of 3 for that one. There's no perfect factors in 3. The square root of 63. 9 times something gives you 63. So the square root of 9 times the square root of 7. Square root of 9 is 3 square root of 7. Any one of those numbers go into 7? No. Simplified, 3 square root of 7. And then the square root of 13 over 36. Separate them. Square root of 13 over the square root of 36. The square root of 13, there's no perfect factors in that. What times itself gives you 36? 6. So the square root of 13 over 6. Again, ask yourself the 3 questions at the end every time. Is there a fraction under the radical like it was here? No. Is there a radical at the bottom of it like we put here? No. And is there a perfect square that goes into 13? No. Simplified. The square root of 48 over the square root of 81. We know the square root of 48 is 16 times 3. We did that one already. Over the square root of 81, you can separate the two, remember, which we know is going to be what times itself is 81 is 9. So the square root of 16 is 4 square root of 3 over what times itself is 81, 9. So check one more time. Ask you 3 questions. Any perfect squares go into 3? No. Is there a radical at the bottom? No. Is there a fraction under the radical? No. One last thing you want to ask yourself when you have fractions, not dealing with the radicals at all, is there a number that goes into both 4 and 9? No, there isn't. So you don't have to reduce the fraction. Had that said 4 over 8, then you would reduce it to 1/2. But we simply have 4 square root of 3 over 9. The square root of 54, when you break it down, is the square root of 9 times the square root of 6. The square root of 9 is 3 square root of 6 over 3. Now you have 3 over 3. They'll cancel each other and simply leave you with the square root of 6. Then the square root of 90 over the square root of 160. Again, separate them. I even read it as being separated. Square root of 160. What perfect square factors do you have? Well, 9 multiplies by 10 to give you 90. And 16 multiplies by 10 to give you 160. So right here you have, look at it, you can, anytime it gets to a point where you can reduce it. You have the square root of 10 over the square root of 10. Something over itself cancels out and leaves you with 1. Now you have the square root of 9 over the square root of 16. What times itself is 9? 3. What times itself is 16? 4. 3/4 for that one.